Well, hey there. Welcome back. This is a follow-up to the Diresta prototype build, mostly about the design and CAD side of things. I hope anyway. But before I get into that, thought I'd take this once-in-a-lifetime opportunity to answer a few questions that came out of the first video. Should you prefer to skip the small talk, feel free to click ahead to this timestamp. No hard feelings. This was fun to build. Now, Diresta and I went back and forth a bit, but finally seeing it take shape, holding it, blasting some dust, taking no prisoners, it was a satisfying build. I look forward to seeing where Jimmy takes it. But I got a lot of questions. Did I actually drill the cross holes through this thing? How did I handle the cam? What do I use to give my hair so much body? First, let's talk about the valve. I got a few recommendations on venting the bottom of the valve bore. I hadn't even considered that and is an excellent idea. So the first round of this design, as I mentioned, had only 2 O-rings. Air could get underneath the valve. A little part of me was trying to be clever, trying to eliminate the need for a spring altogether, using that cushion of air to do the spring's job. I thought I could get away with it since the lever keeps the valve in place, keeps it from shooting out the top. Let's do some quick math to see how much spring force the air would have provided. Don't worry, the math here is pretty simple. To make this even easier, let's assume 100 psi inlet air. The force generated is the pressure times the area that pressure is pushing against. In this case, it's like the diameter of the valve bore, which is about a ½ inch, a ¼ radius, which makes the area about 3 times a quarter times a quarter, which is 3/16, also known as 0.1875. Multiply that by 100, and we're looking at 18 pounds of actuation force. Even if the lever provided a 2-to-1 mechanical advantage, which it obviously doesn't, that's still 9 pounds we'd be up against. You could make the valve diameter smaller so it has less area, so you get less force, but then you'd really start to choke down the airflow and you'd be making smaller, probably more finicky parts. So I abandoned that idea and added a 3rd O-ring to keep the air from ever getting underneath that valve in the first place. There's still air there, but it's not 100 psi. Now it probably adds a bit of force and maybe even slows down the response time of the valve, because when you push it all the way down and you let it go, you're sort of leaving a bit of a vacuum behind. So a vent hole, maybe through the bottom, is a smart idea. Alright, so this is totally unrelated to the airgun build. I should change my channel name to This Old Tangent. I was recently talking to a friend of mine. I was trying to find some old science books for kids that I remember when I was a kid. He had no idea what I was talking about and suggested I might harness the power of the hive mind here on YouTube. I've been slowly exposing my kids to electronics. Their utter lack of respect for Maxwell's equations and Ohm's law is really eroding my trust in the elementary school system. They're 5 and 7, so they're just really plugging LEDs, motors, and buzzers, that sort of stuff, onto 9-volt batteries. We've only just recently upgraded to using buttons and a breadboard. And yes, I'm going through a lot of LEDs. I had gotten to wondering how I, around about their age I suppose, was introduced to electricity and electronics, and it brought back memories of old science experiment books I used to check out of the library. Anyway, I think they were called technology books back then. See, they used to force us maybe once a week to go to the school's library and go through the process of checking out and returning books. In my mind's eye today, it looked like one of those prison libraries you see in the movies. Anyway, I guess I'm looking for help finding old technology books from the 50s or 60s. Not like finding them. I don't really want to buy one. I'd just like to be able to look them up online. Nostalgia, perhaps. I only remember 2 experiments, but I'm willing to bet there's someone out there that knows what I'm talking about. The first I remember, no joke, was a carbon arc furnace for kids. You'd take a pencil, I think, whittle it down with the pocket knife you most certainly just had laying around to get the lead out of it, like the graphite. There's a line drawing of a kid laying on his bedroom floor with 2 clay pots, some wire, pencil lead, and probably blood-soaked hands, but it was black and white so you couldn't really tell. I think the idea was you'd use the 2 clay pots to maintain a gap between 2 pieces of pencil lead while you stripped and hook up line voltage to the opposite ends. I may be missing some details, but you'd flip the switch, and if your breaker didn't blow, you'd get an arc in the pots you could then proceed to burn yourself with if you hadn't already gone blind by that point. You're most likely not going to find science experiments like that anymore. But maybe it was a way to weed out good scientists. like you were probably a good hire in the technology sector because you literally survived your childhood. The other experiment that I recall was an electromechanical combination lock. I'm a bit fuzzy on the carbon arc furnaces. It likely didn't go as planned for me, but this one I remember building. You'd start by spending your first 3 weeks making a solenoid with a big nail and a bunch of magnet wire. You'd proceed to install that solenoid into a dresser drawer. I gotta draw a picture of this for you so you can follow along. The solenoid would stick out one side of the drawer with the nail going into the dresser casework. It would be wired through 3 dials you'd make by pounding more nails into the face of your dresser and wiring them in series from one number to another, the combination that you wanted, probably also powered with mains voltage. When you set like the tuna can tin arms to the right numbers, you would complete the circuit, actuate the solenoid, and unlock your dresser drawer. I remember it actually working. I was quite proud, though the drawer was a little inconvenient to use given that it was now full of wires and probably 30 pointed nails and splintered wood. My apologies for going completely off the rails there. But if you know the kind of books I'm talking about, please let me know down in the comments. Mostly so I can make sure my kids never find them. But since I'm on the subject, when was the last time you looked through science experiments for kids type books? In comparison, they're really quite a letdown. They're all like the rain detector version 4521. Ask your parents for permission to place a plastic cup outside. Order a small rock from Amazon to place in the bottom of the cup so it doesn't blow over. Check back in a couple of days. If it has water in it, it probably rained. Okay, we were talking about the air gun. Drilling the ports. I apologize they didn't make it into the last video. It wasn't intentional. But when you try to get videos down to a manageable length, something's bound to get lost. Making short videos is sometimes quite a challenge. I certainly do want to include every last detail, but sometimes it's just not very practical. In the famous words of Christopher Walken, it's hard because it's very difficult. The holes are 1/8 diameter. Now the outlet side was relatively easy. I already had a large counterbore in order to accept the nozzle that screws into the end. So I was only going about, I don't know, a little bit more than 1/4 of an inch, a half an inch or so. That was no big deal. The inlet side, however, was a little trickier, but still not rocket science. I center drilled the back face before doing any other operation. The boring to accept the taps for the large fittings was done last, and I think you saw that in the last video. But I center drilled, then went down slowly, pecking a lot to keep this drill bit clean, as deep as I could go with the shorter drill bit. The shorter drill bit has a better chance of sort of staying the course. Once that went in about its full depth, I had to switch over to something longer. Now these long, thin drill bits, especially in a mill or a drill press, will use any excuse whatsoever to move off target. So I pecked my way down maybe 1/4 inch at a time, maybe a little bit less, retracting the full drill, blowing the hole out, and coming back in. Now it's very important that these drills are ground properly, that the point is on center. Some of that, with experience, you can tell by ear. If the drill's getting loaded, or if, I don't know if I'd go so far as to say that one flute's cutting more than another, but you'll definitely hear something is not right, at which point you'd hopefully retract the drill in time, clean it out, and go back in. And I slowly worked my way over about 2 inches or so until I broke through the bore. Now, because this is a prototype, I have a little bit more breathing room than I would have if I were working, say, from a print. Where they give me that dimension, and in CAD it's a nice perpendicular line. There's maybe some tolerance on its location. Once I drilled through here, and I finished all the machining operations, cleaned it up nice, and blew it clean, I inserted the drill backwards and just measured the position down from the top of the bore. I wasn't too worried about going off-center, sort of in and out of the part, in the depth of the part. Because if that happened, the valve would still technically work. But if it went up and down any, I could risk porting into the side or above or below an O-ring. As it turned out, in my case, the holes were more or less spot on. But had that hole moved a bit on me, say, I don't know, 1/16 of an inch in either direction, once I took the measurement of where the hole actually ended up, I could accommodate for it on the valve, just moving these features a bit to make up for the fact that the ports moved. Again, I had that liberty here because the entire design was under my control. Had I been working with a print, a hole not in the correct location could potentially be a big problem. So again, with these things, it's a matter of taking your time. Inspect the drill thoroughly, make sure the point's on center and it's sharp, and just slowly work your way through it, keeping it clean, and I guess hope for the best. All right, that's it. Let's get into the CAD and what I meant the second half of this video to actually be.
I don't usually get into CAD on this channel. It's a can of worms, really. And quite frankly, it's usually not that exciting. I mean, don't get me wrong, I love CAD. It's probably the most powerful tool I have at my disposal. More so than the mill or the lathe or the welder. What I mean is, from a purely entertainment point of view, it's usually not that exciting. But what I'd like to demonstrate here, and what the big takeaway from this next segment will be, is parametric modeling. You hear that term thrown around now and again, but unless you really go down into the rabbit hole of CAD, you might not usually see a good practical demonstration of it on a channel like mine. In particular, I want to talk about a method of CAD referred to as master modeling, sometimes described as using a skeleton part. It depends on what CAD package you're using and the crowd you run with. Parametric modeling uses, well, parameters to drive the CAD geometry, as opposed to direct modeling, which is what you might likely do on a simple part, where a hole, for example, is modeled to a specific size, say a 1/2 inch, and it always stays that size no matter what happens to the rest of the CAD, because you've set that size directly. Allow me a quick example. What you're looking at here is SolidWorks, but the actual software really isn't important. Can't say for sure, but I'd assume all CAD these days is parametric. Let's make a 1-inch square plate with a 1/2 inch hole in the center. Maybe we're making a spacer where the design intent is to have a square perimeter and a hole right in the middle. I'll start by making a square and extruding it to thickness. Next, I'll start a new sketch on one of its large faces and make a 1/2 inch circle, dimensioning it so it's 1/2 inch from each side, putting the hole right in the middle of the 1-inch part. I'll use the circle to create a cut, and there we have it, a square plate with a 1/2 inch hole right in the middle, just as we intended. But let's say something in your build changes and you really need a 2-inch square plate. Let's go in and update the first sketch to make it 2 inches. As soon as we exit the sketch and the part updates, we'll see the hole is no longer in center. It's still 1/2 inch from each edge. That's not what we wanted, but that's what we told the CAD to do. It's not the CAD's fault, it's doing exactly what we asked it to do. This is a consequence of direct modeling. Let's go change the square back to 1 inch. It'll update and we're back where we started. Now let's edit the sketch for the hole. Instead of dimensioning its location, we'll use what's called construction geometry to set the hole on center. Basically, I'm using these sketch lines to fix the position of the hole in the middle of each edge. One of them's horizontal and the other one's vertical, so as a consequence, the hole will always be in the middle. It might seem like a trivial change, but what we've done here is built-in design intent. We always want that hole to be on center, no matter the size of the plate. Notice there aren't any dimensions other than the size of the hole. Now, if we update the square sketch to make it 2 inches again, let's see what happens. Perfect. Still on center. Let's make it 5-inch square. Again, since the location of the hole is based on the center point of the edges, no matter what size we make the plate, the hole always ends up where we intended it to end up. The CAD model, instead of using explicit dimensions, is now using our parameters, for lack of a more exciting word. And more importantly, maintaining our design intent. The model is a little bit smarter than it was before. It's a little bit smarter than it was as a direct model. If you were, say, a manufacturer of fasteners, you make nuts and bolts for a living, you most certainly would not want to direct model all of the hardware you make. The sane way to do it would be to make a generic model that represents maybe one of each of your products, say a socket head cap screw, and then you might use a spreadsheet, a database of some kind that contains all of your combinations of parameters, such as bolt diameter, head size, thread pitch, etc. That way when you need CAD of say a 1/2 inch 13 bolt, the CAD software would already have a skeleton of the bolt ready and simply read in the dimensions from the database to generate the specific CAD for that fastener. Although that's another level of parametric complexity, hopefully it illustrates the idea of a smart CAD model. Let's get back to our square spacer. In particular, let's take a look at the CAD history. In this case, SOLIDWORKS calls it the feature tree. I'll expand the 2 features we made, and it'll show the sketches that each feature is driven by. The first is the square that creates the square plate, and the second is the circle that creates the hole. The feature tree is a timeline of what you've done in CAD. The further back in the tree you go, the further back in history you're traveling. You're sort of going back in time. And we want to work smart so that any changes we make back here in the past propagate forward correctly to the future, or to the bottom of the tree, resulting in the part you intended to make, and ensure we don't erase ourselves from all of our family Polaroids. Okay, so back to the task at hand. I'll go through this pretty quick. Again, the mechanical design isn't the point here per se. I more want to share the CAD methodology, but I'll talk you through it. I started off by bringing in Diresta Sketch and scaling it to the one dimension I do know, the 1-inch holes. From there, I start to rough in the geometry, starting with a schematic valve and then branching out a bit. I want to get the overall design into the CAD space, and I'm keeping an eye in particular on what will become the internal walls, like the space between features. This sketch is effectively the cross-section, and I know I'll be machining it, so I'm trying to leave myself some breathing room while still keeping the design as tight as possible. Once I have a handle on the space I'm working with and the general layout of the features, I turned my attention to the valve. At this point, it's a best guess. I'm throwing some numbers around by eye, working on instinct really. Later, when I have an assembly of parts, I can come back in and fine-tune everything. The valve turned out to be a little more problematic than I'd sort of envisioned beforehand. I didn't have enough space in the body to take advantage of all of the lever throw. I mean, I could have made the stroke shorter, but that'd probably feel weird. Or I could have made the valve deeper, but that would result in a bigger blowgun entirely. So with pain in my heart, I angled the air outlet to buy me some space. This is great in CAD, but now I'm going to have to machine a small, deep hole out of square. Lastly, I moved on to the lever. Again, mostly doing this by eye. I'll have a chance to check the clearances in the final assembly. Not sure if you can make it out, but I'm trying to bake the geometric relationships right into the CAD so that later, if I need to change something, hopefully the rest of the geometry updates and follows suit, saving me a ton of time trying to remember why I made certain features the way I did, and hopefully also minimizing any potential errors that could creep in while I'm making changes later. With the general overall form laid out, I can add some key sketches that will later establish the thickness of the part in critical locations and give me somewhere to hang my hat, for example, in the lever's hinge area where there's a little bit more, I guess, 3D or depth information required across parts. And with that, the CAD Master is probably 95% finished. Again, I'll be coming back to this sort of master file to make any changes to the parts we're about to see. So it's usually an iterative process. Get as much detail in the master as possible, make the parts, if I'm missing some information, come back into the master and add it, etc. Now notice there aren't any solids or surfaces here. No extrudes, no cuts, no revolves, only sketches. There are times when more information is useful, but this isn't one of them. All of my sketches live here. All of the design intent is here. Just about all of the work is technically done. It's just a matter of spinning off the discrete parts. This next part is important in the workflow, so I'm going to slow down a bit here. I apologize for that last segment. Probably made you dizzy watching CAD move that fast. But CAD fast, die young, that's what I say. Everything you saw up until now was probably, I don't know, an hour of CAD time. About a mug and a half of coffee. If I had talked you through that, we'd be looking at probably a 2-hour YouTube video. So hopefully you understand. Okay, up until now I've been working in one part file. The file you saw is the only file I have in CAD so far. And as you've seen, it's only sketches. Well, sketches in planes. And I've called it Knuckle Master. Now I need to use that file to create all the discrete parts. I'll start with the body. I've made a new file, a new part, totally blank, and I'm going to insert my master part. In the feature tree now, I've nested the master. It's a single entry, but it contains all of the information we were just working with. This part, what will become the body of the blowgun, is now dependent on the master. Think of it like the DNA for this new part, the instructions needed to build it. In this body part, I can now pick up the information I need and start creating a solid. If for any reason there's information, say another sketch, that I'm missing, I would go back into the master, add it there, and when I came back here, it would magically appear. Now I can walk my way through adding and sizing features accordingly. I'm doing this quote-unquote live, by the way. I'll probably come back in and clean up some of these features, adding correct dimensions for, the holes that I know will end up being tapped, for example, and making the aesthetics look right, or look better. Some of these features I'm just throwing in to get the point across. I hope you get the idea. I can now make the rest of the components in exactly the same way, starting each new part with the master document at the top of the feature tree, picking up the details I need for that particular part, and building them out. Finally, all the parts are brought together in an assembly file. Here I can set the allowable motion for each component and, in a way, virtually test the thing out. Case in point, here I can see I need a bit more stroke in my valve, or I need to bring the O-rings a little closer together. Now, this still needs about another half hour or so of work. I need to fix that valve issue, size the O-rings properly, clean up some of the fits for the moving parts, double check all the bore dimensions. I think I'll thicken up some of the thinner parts you see in the body of the blowgun. They look a little thin. And I'd like to reduce some of the blending that happens between the transitions. Add a touch of sexy to it. Again, all of that should be relatively easy to do since I'm working with a master. I'm taking advantage of the parametric CAD. If, for example, I change the valve diameter, the bore it sits in, along with the O-rings, will all update to that new size. Had I modeled all these parts directly and then brought them together in assembly sort of independently, I'd have to update each discrete component one at a time and hope I didn't make any mistakes.
You might have noticed that this finished part looks a little different from the CAD we just saw. And that's because it is. There was another iteration between that CAD and the final CNC work. Jimmy opted to roll the holes forward a bit. That shortened the overall blowgun, going to more of a snub nose or a bulldog look, in exchange for a slight increase in overall height. It was subtle, but not only do I think it looks better, it gave me just enough height back to correct the angled bore on the valve outlet. Now, all three bores are perpendicular to each other, making fabrication that much easier.
And with the master model strategy in CAD, if done correctly, changes like that usually aren't a big deal. I mean, within reason, of course. Let's take another quick look at the chain of command here. I started with a single, simple part, only sketches, sketch geometry, and planes, which is the master. Again, all of the information for each part lives here. That master was then inserted into new parts as their first feature that became the discrete 3D components, say the body, the valve, and the lever in this case. Those parts in turn were brought into an assembly file where I could check the design for its function, fits, interferences, ease of manufacture, maybe that sort of thing. Any changes that fundamentally impact the entire design, I'd make back in the master. And those changes would trickle through the parts and show up in the final assembly, without having to go into each part manually and update features that change would affect. On the other hand, small changes that only affect one single part would happen in their part file. If I wanted to change, say, a cosmetic radius, for example, at the top edge of the lever, I would do that in the lever part and it would trickle down to the assembly. No need to do that back in the master since it really only impacts one single part. Let's have a look. Let's make a few changes. Say, for example, the finger holes are a little big at 1 inch. We'll bump those down to 7/8. Maybe we also want a bit more airflow, so we'll increase the valve size a smidge. In real life, you'd want to make sure that you can actually find O-rings of the size you just made up. And I don't know, perhaps we raise the height of the lever a bit, giving it a little bit more curvature at the top. Now, if we jump back into the assembly, we'll see the gears turning and the smoke rising as the CAD updates all of the parts that were driven by the sketches we just changed. If I had 2D drawings of all my parts, those of course would also update. While I have you all over here at my house, let's also take a quick look at the cam. Again, I personally use Fusion 360, and switching over to Fusion breaks the parametric chain for me. I import a step file that I saved out of SOLIDWORKS, and that step file becomes my starting point in Fusion. The master and the sketches we saw before are effectively lost now, or lost here in Fusion. Step files are dumb solids with no feature history, so I can't really change anything, though Fusion does have some direct editing tools that allow you to modify the model to some extent. If you wanted to make the body thicker or thinner, or change specific features, you could do that in Fusion, but that obviously wouldn't propagate over to anything else. I could make the bore smaller, but then the valve wouldn't fit because the valve doesn't know the bore got smaller. Now, had I modeled everything in Fusion to begin with, the cam would also be parametrically linked. The cam would also be part of that entire design chain. Meaning if I change, say, the grip size of the blowgun body, not only would an assembly update in Fusion, but the cam toolpaths would also update. Losing that parametric connection is the price I pay for switching between systems. The cam for this part is pretty straightforward. 2D adaptive toolpath clears out the holes in the body of the blowgun first. That's followed by a 2D contour that leaves a few tabs behind to hold the part for the secondary operations on the other side. Another 2D adaptive creates half of the hinge at the top before taking one side down to final size. Finally, I used a scalloped toolpath to clean up the cylindrical areas with a ball nose end mill, and then do a 2D chamfer with a chamfer tool to, well, add the chamfers. I did have to remove the chamfers I had modeled in SOLIDWORKS. You can see they're missing on the step file here, in order to use the 2D chamfer toolpath in Fusion. I'm sure there's a way to cut the chamfer while it's actually in the CAD, in the 3D geometry, but I couldn't figure it out. And finally, you might have noticed that I'm not using any finishing operations here, which I probably should have. Should have left some material behind on the roughing passes and did a final cleanup cut. But it's a prototype and I wanted a chance to use my new sandpaper app.
Alright, well I think that's about all I got for you today. It was a little bit of a long one, so if you stuck through all of that, thanks for watching.